This video will look at solving quadratic equations using the square root method. You can't always use the square root method, but the time you can is when you have your standard quadratic equation you're used to seeing like this. When you have a quadratic equation that has no bx term, you can use the square root method to solve this. So let's look at example 3, and you will see how straightforward and handy this method is to know. If you have 3x squared plus 5 equaling 41, all you need to do is solve for x. The good old-fashioned way, using inverse operations and isolating your variable. So I will subtract 5 from both sides, and I end up with 3x squared equals 36. Continue to isolate x, in this case x squared, so we're going to divide by 3, and you are now at x squared equals 12. Well, now when you're here, in order to undo a square, you just simply square root it. So I will take the square root of both sides. And this is a situation in where your positive and negative root need to come into play, because both of them do exist. So when I square root x squared, I end up with x, and then I have plus or minus, and that's how we write it to represent the two roots, the square root of 12. You would think you were done, except you have not completely simplified your radical. You have a perfect square factor of 4 hidden in the 12, and so you could write it out as plus or minus the square root of 4 times 3, and then square root the 4 because it's perfect, and there you end up with your two roots, which are the answers. And when you think about it, it should make sense that you have two answers for what x could be, because you have two places in which the parabola crosses the x-axis. Let's look at example 4. It says, what are the solutions of this equation? 1/5 z plus 3, that whole quantity squared, equals 7. So I will solve this off to the side and rewrite it. If we have 1/5 times the quantity z plus 3 squared equals 7, this one you have to tackle in just a different way, because it's this entire quantity that's being squared. So I need to isolate this before I can square root it and find out what z is. So we'll begin by undoing the 1/5 times that quantity, and we undo that by multiplying by the reciprocal 5 or 5 over 1, however you see it. And then you are left with z plus 3 squared equals 35. And now you're ready to square root, because there's nothing else you can do, and that whole quantity is isolated. So square root both sides, and then you are left with your next line, z plus 3 equals plus or minus the square root of 35. Now you have to be careful in situations like these, because you just kind of have to see them differently too. I still need to isolate z, and so at this point I still need to subtract 3 from both sides. And when you simplify that, you're left with z equals negative 3 plus or minus the square root of 35. 35 has no perfect square factors in it, and so you're actually done. You're still going to have two answers. If you did this on your calculator, you would take negative 3 plus whatever decimal that was, and then that'd be one value for z, and then you would take negative 3 minus the square root of 35, and then you would see, if you were doing it on your calculator, what the decimal version is. But in this case, they left the answer as is. Here are your two equations, or your two expressions that are solutions to this equation. Here we have some guided practice problems where you can use the square root method to solve this quadratic equation. So pause the video now and press resume when you're ready. And here are the answers to the square root method for quadratic equations. And these two are pretty straightforward. I think you can just look at them and see what's going on. Number 19 is a little more complicated. We need to divide by 3 first in order to isolate this binomial. And once we do, we can square root it, leaving us with the positive and negative root of 40 over 3. And then we add 2 to both sides, leaving us here. But this one is not totally simplified because you cannot leave this square root of 3 in the denominator. So this is a situation where you need to rationalize the denominator to get that radical out of there. And you also have an issue with this 40 having a perfect square factor in there. So we will do one at a time. So I will rationalize my denominator, leaving me with the square root of 120 on top. That's 40 times 3. And now I just have a 3 in the denominator because the square root of 3 times the square root of 3 is just the square root of 9. And then we need to go further because 120 has a perfect square factor in it. 4 is definitely in it. So I know that I have x equals 2 plus or minus. If I have a 4 in it, it would be 4 times 30. I'm going to square root that 4 right away, so it comes out. The square root of 4 is 2, leaving me with the 30 over this 3. Sorry, I have to write into that problem. 30 has 3 and 10, and none of those factors would repeat, or 15 and 2, and none of those repeat. So, oops, and I made another mistake because this does not go over that first term. So it's 2 plus or minus 2 times the square root of 30 over 3. And you are done at this point. And so we will, oops, put that around there and say that we're done. All right, square root method brings us to our very first vertical motion problem. This is real life. Math applied to your physical world around you. And the real world application for quadratics is when you have an object at the top of the building and drop it down. And so up here you can see that if you were here, I guess your window washer, and you drop something down, straight down, it would go. But if you recorded this versus time, the time factor elongates this kind of motion and brings it out to the side, creating a parabola when you're doing your height versus your time scale. And so here's kind of half a parabola. And there is an equation that goes with these vertical motion models when an object is dropped. And that one is this right here, where it says h equals negative 16t squared plus h naught. And that is how you say this. So we'll go through this one thing at a time. This h is your height after a certain amount of time of the object you dropped. The negative 16 is gravity's acceleration in the down direction in feet per second. Time squared right there is self-explanatory. And h naught is the initial height that you drop the object. So whenever you see this little sub-zero, it means initial something, either initial velocity or initial height. And so if you are encountering a problem where an object is dropped, you immediately need to know that you need to go and pick out this equation to solve for the height after a certain amount of time. Here is an example that will use the vertical motion model. It's a science competition, and students have to design a container that prevents an egg from breaking when dropped from a height of 50 feet. So perhaps you're on top of a building and you want to let this egg go, and you want to know how long does it take the container to hit the ground. And so again, instant you see something is being dropped, you need to think vertical motion model, and you write it down. So h equals that negative 16t squared plus h naught. And fill in what you know. If you're looking for how long the container takes to hit the ground, the thing we are looking for is t. The initial height it is dropped from, or sorry, yes, the initial height it is dropped from is 50, so I'm going to fill that in because I know I started 50 feet high, and fill in everything else. Now you need to kind of think intelligently here, and the question is, how high are you after this thing hits the ground? Because you're looking for t when the object hits the ground. In that case, you need to know that your h, the height you're looking for, is 0. How long does it take the egg to start from 50 feet high and hit the ground? So your final height is 0. Your initial height was 50. And it doesn't always work that way, but just be aware that it happens a lot. So now we have to solve this thing for t squared, and it should be easy to notice that you have no middle term, no t to the first power. So we can use the square root method to solve it. So I will subtract this 50 from both sides, and you are left with negative 50 equals negative 16t squared, and continue to solve for t. Your negatives cancel and you're left with 50 over 16 equals t squared. And then to solve for t, you would square root both sides. And you would need to simplify this if we were leaving it in simplest radical form, but since we're talking about something that we actually might be interested in, how long it takes the egg to hit the ground, you can use your calculator on situations like these and just take the square root of 50 over 16, and you will see that you get that your time is plus or minus 1.8 seconds. And then because this is a real life problem, it doesn't make any sense unless you're magical that you can go back in time, so you can't go negative 1.8 seconds. So you would kind of cross that solution out, and your final answer would just be that it took 1.8 seconds for your egg to fall 50 feet and hit the ground. You could do guided practice number 20. The only thing that's changed now is that you're at 30 feet high, and so your H naught will be 30, and you could go ahead and solve that. All right, as always, if you have any questions, you can come see me, or if anything confused you and you think watching the video again would help, by all means do so.